This is homework hints for homework number 32 from page 157. So the question asks us to reason about the orthocenter of a triangle. So I still have my tools that will help me create orthocenters. So I've got a triangle, and then I'm going to use my other tool to create the circumcenter and circumcircle. And I'm going to show the orthocenter, and I'm going to show the I'm going to just show the orthocenter for now. So the homework problem says that there's something special happens if you take and reflect the orthocenter across each of the three sides of the triangle. So I'm going to take the label off so it doesn't get in my way so much, and I'm going to reflect the orthocenter across one of the sides. So I'm going to transform and reflect. And that point falls outside the triangle. The conjecture is that that point will fall on the circle that contains the three vertices of the triangle, or the circumcircle. So I'll turn that on to see, and it looks like that indeed happens, so that's good. Now the proof is the question asks you to prove that this point will fall on this circle. And then once we can do that, we should be able to do a very similar proof to show that if we had reflected this point across this side, it would have still fallen on this circle. So a suggestion is, rather than reflect this point, let's imagine reflecting the line segments that connect the vertices to the orthocenter. So I'm going to do this again. I'm going to say, let's redo this reflection. And when I do that, I get this line segment reflected outside and this line segment reflected. And this is a reflection, which we know is an isometry, which we know preserves distance. So what we can conclude from here is that this segment here is the same length as this segment here, which means those two segments are congruent. Similarly up here, I've got this segment to this segment. So those two things are congruent, and finally I have a third piece that's congruent to itself, and that gives me this triangle and this triangle are congruent by side, side, side. Then I can conclude that the corresponding parts are congruent, so I can conclude that this angle here is congruent to this angle here. So I think that should be a helpful start. Unfortunately, I think the next step is sort of out of the blue, so I wanted to show you this so that you didn't get totally frustrated with this problem. So the next thing that I'm going to do is reflect this point over each of these lines, or I could just extend these sides. And now when I do that, I created a whole bunch of other stuff, but the thing that I'm most interested in right now is a quadrilateral, and it happens to be this quadrilateral here. So if I draw my attention to that quadrilateral, the first thing that I notice is this angle here is a vertical angle to this angle, so I have congruent angles here. The next thing that I notice, or that I should remember, is the way that I constructed the orthocenter should remind me that this angle here and this angle here should be right angles. So now we've got a quadrilateral, and we know something about three of its angles, which means we should sort of know something about the fourth, namely that if I added these three up and subtracted that sum from 360, I'd get the measure of this angle. So if I pay attention to this angle, I think we're almost there. So the point here is to say I know that these two angles sum to be 180 because they're two right angles. So what would that tell you about the sum of these two? So whatever you can say about the sum of these two, you can make the same claim about the sum of this angle and this angle. or possibly more importantly, this angle and this angle. So if you can make a claim about the sum of this angle and this angle, you should be able to make some claim about this quadrilateral, which should help you make a claim about this point here. So I hope that that's a sufficient amount of help for this problem. Like I said, I know it's a difficult one. Remember that that just shows that one of those points reflected across will fall in the circle. I don't know if I need full detail on the others, but you could at least show me where the picture, or show me where the parts would be. But it should be a very similar argument.